joining online today. Everyone's anxious to get away for spring break. Um, Hope everyone has a fun and safe and relaxing, rejuvenating spring break. I'm uh, hoping to spend a little bit of my spring break fly fishing in the East Coast area and make my way up to New York for the week after spring break. So I may or may not be on site teaching the week after spring break. And so I'll update you. I did just come down with a little bit of a cold, so my plans may change. But hopefully, I'd love to get to New York. My daughters live there. I'd love to see them. And yeah, I'd love to meet you guys face to face. So try, if possible, to be in class in person on the week after spring break. But again, I'll keep you updated. All right, so yes, we had an exam, and I think we did pretty well. I think we're reasonable in terms of the averages there. Um, you I don't know if you've already seen your midterm grades. I posted them for this class last night. And about now, sometimes people are realizing they're in a little bit of trouble. This is a required course for EE, so we want everyone to graduate with and finish this class with a good grade. The big thing to focus on is your MATLAB assignments. Those are, I think, 30% of your grade in the end. So um, uh, some of you are not totally current on those. So the first step is to get current on those before you ask for any extra credit or anything like that, right? After that, if people are still in trouble overall, I will entertain the idea of a little mini project that would probably be based on GNU Radio, which is a software-defined radio. So, I had hoped to incorporate that in the labs and the course, but I just keep feeling like it's too much to ask in this short of a course for everyone to do. But if you are needing a little bit of extra points in the course, I will entertain that. GNU Radio is basically a way of actually implementing the radio algorithms in software, predominantly software. And normally you're going to have a lot of hardware still around that you need an antenna, you need some amplifiers, you need some A to D converters and D to A converters and that type of thing, right? But there are some ways that we can work with GNU Radio in a software only type of situation. So um, uh, if you are thinking you need help in a course, as I say, the first thing is to get all your assignments in. After that, if you still believe you need some help, then we can talk about this as a way to kind of boost your grade. It's not going to do miracles for you, but I think it's a great learning exercise, and it is reasonable to do. You will not want to wait till the last minute because it can take you a week just to get it set up on a computer type of thing. So anyway, I'm tossing that out there. Let's go ahead and review the exam, and we'll go through that real quick. Midterm exam, right? Is that showing the right thing? Okay, so we did pretty good on this. Just put down your units there. Note that when you're seeing this type of equation, think through whether you should be using the value in linear terms or in dB. I think I cautioned that in the either the previous lecture or the preview or something like that, right? So, and then, yeah, I kind of helped you out with the log base too. Sometimes it's easy if you know that factor inside there is 8 or 16 or you know something that's easy to do a log base to it, but log base 11 or log base 21 is a little trickier. So we did pretty well on that. We did pretty well on problem 2 here, right? So that you can use the equation here, the idea that if this probability of inside here is lower than the log is lower, but when you negate it, it's going to be higher, right? So then, okay, here, boy, read the question. Make sure you try to, you know, solve the whole problem, right? So this one, we went over how to generate a 3-bit code, and uh, then then it's a matter of assigning it. Turns out you can just kind of start somewhere and just go clockwise or counterclockwise in that order. It's not always a given that like this one would be gray with respect to this one, with respect to this one, with respect to this one. But you also need to make sure that these guys are also. But it works in this case, right? So it gets more difficult with larger and more complex constellations and that type of thing. So yeah, so I think a lot of people got this right. The decision areas, again, you're looking at the closest ones, right? So we're going to assume that the closest constellation points are the ones that we need to worry about. And this guy over here, relative to this one, is less of a concern, right? So we would draw a you know, and okay, so we're there's an implicit assumption that it's equal probable symbols here, right? So we would look at the lines connecting these guys and then draw in orthogonal bisectors of these lines, right? So you could maybe have a dotted line connecting here and then draw in something that's perpendicular midway, right? Bisecting it, and then do the same here, do the same here, and so on. And you should end up with something like this, right? All right, then we did pretty good here. Yeah, this year I tossed in this, and a few of y'all got a little confused on that. Yeah, I'm not trying to trick you up, but I'm trying to make sure that you understand what are the right variables to plug into these equations, right? So most people identified the correct equation. It's just that it's the data rate that is going into this, not the carrier frequency. So then this gave us some trouble. The big deal here is that the map of the maximum a posteriori receiver is more general. It can handle cases where we don't have equal probable symbols, and you have that bias term that you can incorporate, and it's added as a sum in that overall block diagram, right? So you're adding a signal there before you start doing your thresholding. The maximum likelihood receiver requires that we have equal probable symbols. So there's an implicit there's an assumption in there in the derivation of the maximum likelihood receiver. So all right, then this last no, that's not the last one. So this one, the system is not equal probable. You know, I give the probabilities here, and you can, you know, since it's a binary system, there's two symbols here, and they're binary antipolar. as you see up here. And then you can use this equation here to plug in, and so identify which uh, decision area you're working with when you're deriving this threshold, and then plug in the appropriate probabilities for that. The N naught and EB end up well, they're given there, and so you get a small negative bias here, and that means that the decision area D1 is actually larger, right? Because for equal probable signaling, your threshold would be at 0. There's A and minus A, and so if they were equal probable, it'd be right at 0. Instead, it's going to be biased to enlarge D1, right? So since we know a priori that D1 is more, or S1 is more likely, we kind of favor that by expanding the decision area D1, and that helps us make the right decision more often. So then, and a few of y'all used tried, plugged in here. This gives you the bias, and you're almost there. So I give you credit for that. This is like taking all this information and deriving a specific threshold for that decision area. Then here, fill in the blanks. This is meant to be kind of a easy 2 points for you, kind of crunch it out. Most people got these. This is just kind of reinforcing the concepts of a bandwidth efficient modulation, right? So here, if you have, let's say, 2 bits per symbol, then you're for every symbol you're sending 2 bits, right? And so your bit rate for bandwidth efficient modulation should generally be equal to or larger than your symbol rate. A few of y'all got that flipped, and you got most of your credit, but not all, right? So you're simply looking at these bits per symbol and factoring that out. Just kind of work it out in your head that the idea of this bandwidth efficient modulation is to send more bits per symbol, because the symbol rate is what determines the bandwidth of the waveform out in the spectrum, and that's generally what we're constrained by, right? So the FCC or Ofcom or whatever regulatory agency says you can have this amount of bandwidth to work with for your communication system, and you've got to stay within that. That's determined by the symbol rate, but we'd like to send as many bits we can within that constraint, right? So that's why we end up using this bandwidth efficient modulation with this M-ARRI type modulation. All right, then this, I think we actually did really well on this one also. The idea here is that, yes, these 2 receivers are both potentially optimal, but and they're identical. If they're both optimal, then they kind of have to be identical, right? But actually only at the instant that we sample it, right? So in this case, each time we integrate, we're going to kind of, integration is a summation over, in this case, time, right? So each time we sample it, we're going to zero out this argument here in the integral and start integrating again. Whereas here in the match filter, it's a convolution that just goes on and on and on forever in time, right? So that is going to mean that in between things, they're might be very different, but at the sampling instant, they're going to be the same. right? So here everything gets reset to 0. Here we tend to kind of add or subtract to that overall sum that's part of that convolution, depending upon whether this is, kind of positive going or negative going, right? So then here, again, make sure you try to do all of the tasks here. All right, the things to pick up on here is it's equal probable, it's quadrature, and it's binary, right? Binary means we have two symbols. I give you the two symbols, right? There's S1 and S2. So S1 here in this complex notation, this would be the real part, this would be the imaginary part, or what we oftentimes call the I part or the Q, the in phase. The I stands for in phase and the Q stands for quadrature. So we could label these axes, the I axis and the Q axis. The S1 would go here, S2 here. Some of you all put it down here in a negative area. I'm not sure why. But again, the idea is that there's two symbols. Some people tried to put a whole lot more symbols than that on there. No, it's just binary signaling. The quadrature doesn't mean there's 4 of them or anything like that. It just means that these symbols are in quadrature with respect to each other. So speaking of quadrature as a mathematical concept, when you correlate these two, there's no they correlate to 0, right? And then I give you the signal noise ratio, or the EBNO, in linear and dB form. So then you can, since it's binary, you can use this equation, right? Where we derive this equation in class, and we have this distance metric between the symbols, but that can be related to with this rho, this correlation, cross correlation factor rho. And here the idea is that it's in quadrature, right? So here this guy's working on the real axis, this guy's working on the imaginary axis. You look at these two things, they are in quadrature, so there's no cross correlation. So that if you pick up on the fact that rho is 0, then this problem becomes pretty straightforward. You just plug in 0 there. Now you've got d squared 1, 2 is 2 times the energy. So you put that in there, the 2's cancel. You've got EBNO, since it's binary system, EECE equals EB, so we don't need to do any conversions there. So that's given as 16. The square root of 16 is 4. You look up Q of 4, and it's 3.1671 times 10 to the minus 5th. So hopefully that makes sense to everyone. And so let's go ahead and go on to our lecture for today. Actually, I'll just share the entire screen. Okay, so we did the exam review, and so last year, based upon that that exam, I kind of had some feedback to give to the students. I decided to keep that in this semester also because I think it's really good information. And then it had been a while since I taught, and so I was I'm trying to make sure that our expectations are matched up with what I think you should know. Most of this is informed by my industrial experience, right? So I spent most of my career in industry. And so here's just some ideas. Now, don't beat yourself up on this if you're a second semester double E senior and you're not confident in one of these things. I'm not saying you got to know these things, flat out, but these things ought to be within your intellectual reach, right? So you should be able to determine units of an answer in an assignment, in a exam. You should always be thinking about what are the units, right? And making sure that you're following the metric prefixes. Mega is a million, gig is a billion, kilo is a thousand, and so on, right? You should know a lot more than that. Maybe you don't know atto or femto or something like that. That's okay, right? But you should know the basics. Period is a reciprocal rate. I think we did pretty well on this. Just the idea that rate is really a frequency type of thing, right? So frequency and period are reciprocals of each other. The output of a linear system is the input signal convolved with the system's impulse response, right? So that's your basic linear systems analysis. You probably did a lot of this last year during your junior year in your signals and systems class. Maybe you're doing it in your control systems class right now. The output of a linear system is the input signal, and we're talking in the time domain here, convolved with the system's impulse response. So you can take a system that in communication systems that might be a filter. In other systems, it might be something more complex, right? But we can measure the system's impulse response by hitting it with an impulse, right? And then looking at or measuring the output time domain, right? So convolution is done by flipping one factor and sliding it across the other while summing the area under the intersected region. Right, so we talked a little bit about the difference between correlation and convolution. So just reinforcing these ideas as kind of foundational, fundamental type of things, right? Okay, so then in the frequency domain, we can multiply the input frequency response with the frequency response of the system to produce the output frequency response, right? So in the time domain, we're convolving. In the frequency domain, we're multiplying, right? And oftentimes, it's actually easier to go ahead and take the Fourier transforms of everything so that we can multiply, because multiplying tends to be easier than convolution, even though we've got to do these Fourier transforms. Well, we get pretty good at doing the Fourier and inverse Fourier transforms, so that's okay, right? So the frequency response of the system is a Fourier transform of its impulse response, right? So now here we get into some, more thoughtful top things. Hopefully all this stuff is pretty foundational for you at this point. Steep slope in the time domain is reflected by high frequencies in the frequency domain. So think through that. When you have things that change very rapidly over a short period of time, that's kind of implying a very high frequency type of thing, right? So just that becomes intuitive to you after a while. You see sharp things in a time domain, you're thinking, wow, that's a very high frequency or wide bandwidth type of thing in the frequency domain, right? So all right, here's another thing. You probably studied this one to death last year in your signals and systems course, but a square wave signal is, if you do the Fourier series expansion of it, right, you will then find that it can be, replicated. The square wave in the time domain can be, replicated in this Fourier series expansion with the infinite number of odd harmonics at progressively lower amplitudes, right? So you have all these different odd harmonics, right? So each odd multiples of the fundamental frequency of that square wave where each amplitude is like it's 1 over the harmonic, right? So that exact formulation isn't a real issue. It's just that if you have a square wave in the time domain, it takes an infinite amount of spectrum to uh, to transmit that, right? So that is a problem, as we're going to see in today's lecture, right? So convolution of two rect functions produces a triangle, right? So think about that. If you've got a rectangle, let's say a pulse, and now you send that through um, a filter or something that has a rectangular uh, 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 time domain impulse response, then the output's going to be that a triangle, right? So the Fourier transform of a rect is the sinc function, right? So you probably remember that. This sinc is just shorthand for sine x over x. Sometimes it's sine nx over nx. The triangle then ends up being a squared thing of this. Also, yeah, this is also a fundamental thing that you should have learned in applied electromagnetics or your physics courses, that the velocity of a wave is equal to its frequency times its wavelength. I'm not sure we're using that at present, but that does come into play a lot in communications. All right, a few other things. Relationship between decibels and linear units. Yes, always be kind of aware. Does that formula, is it looking for a linear form, or is it looking for the dB form, right? The decibels. And we just use decibels a lot because the dynamic range of some systems can be quite large, right? So if you're working in linear units, then you've got simultaneously, you got to deal with really small numbers and you got to deal with really large numbers, right? So decibels, converting that to decibels allows us to kind of compress that range, and also allows us, instead of having to multiply things, if we got a gain stack up of multiple amplifiers and maybe some things with some loss to them in a system, we'd have to multiply all those. But if we translate those to dB, then by those properties of logarithms, we can add or subtract instead of multiplying or dividing, right? So you should be used to this. Of course, A here is because this is multiplying by a factor of 10, we can infer that A is referring to powers. If it's referring to an amplitude that might be dimensioned in volts, then we would have a 20 out here, right? Because we're really kind of squaring that to get to power. And so if we have a square in the argument of a logarithm, we can pull that exponent out as a coefficient of the log operation, right? So this is just reviewing logarithms and convert back and forth, right? So multiplying and dividing numbers with a common base is equivalent to adding or subtracting their exponents, right? These are just things, hopefully you know these. If not, they're kind of sparking your memory a little bit. The dot product, all right, so you probably did this, and I think you still have a mathematical methods course, but you probably study it in Calc 2 or 3 or something also, right? So dot product is used to determine the projections of a vector onto the basis function or coordinate axis. We've already used that a couple of times in this course. All right, so that's kind of review, just to make sure that we're all on the same page. If you think I've got an unreasonable expectation that you know these things, then yeah, let me know, and we can certainly review these things, right? So as you practice as engineering, all these things become very intuitive to you after a while. Right, then here's some things that I tossed in that impressed me in an interview. Now, this is in a certain context. I've done a lot of AI work in leading AI teams, machine learning teams, and maybe these questions don't have as much relevance there, but I've done tons and tons of signal processing and communications work, and these things are definitely important there. But understanding that with the Fourier transform process, you completely trade off resolution in the time domain for resolution in the frequency domain. Now, this didn't really dawn on me until much later in my career, even though I was originally a filter engineer and dealt with Fourier transforms all the time, right? But in the when you're working in the time domain, in the per time domain, you really, you're looking at a signal, let's say on an oscilloscope. You don't have any frequency information. Maybe you can infer it because you're seeing things that are moving very fast in a time domain, but you're kind of doing your own little Fourier transform in your brain then, right? But if you're just looking at an equation or a signal and you're in a time domain, all frequencies are represented in that time, right? If you look at an instant of time, you got all frequencies right there. So you have no resolution in time. Conversely, when you map it, you transform into the frequency domain, you lose all your time resolution, right? So all your time information. You don't know, looking at a frequency response of a system, when a particular signal happened in there, right? So there's actually some assumptions that you make about stationarity and that type of thing when you're doing this type of thing, particularly with uh, signals that are varying in time, right? Um, but yeah, so there are actually some transforms like the wavelet transform or the short time Fourier transform that we can kind of get a compromise so we can get a little bit of frequency resolution and a little bit of time domain resolution going on so you can kind of see what's happening in time while you're looking at frequency and vice versa. But with Fourier transform, you're one or the other, right? Um, so things that are bounded in the time domain are unbounded in the frequency domain and vice versa. Now, this is very important and very foundational, and we're going to use that uh, today in the lecture. So, if you have a signal that's um, uh, you know starts at a particular time and stops at a particular time, and then there's no more, right? Then that when you do the Fourier transform of that, that you're going to find that that spectrum goes off forever, right? It has an infinite spectrum. Vice versa, if you try to have something bounded in the frequency domain so that it only has frequencies that exist within a certain region, then your signal in the time domain is going to be infinite. It's going to be unbounded, right? So understanding the assumptions we often make and their implications. This is another important one that I've always kind of reinforced with the engineers that I mentor professionally, and particularly as you get into graduate school, but even as seniors, right? So when we first learn things, we often make some assumptions that things are linear, that they're time invariant. If you look at circuits, you're assuming that all the effect of that capacitor is all centered at a particular node spatially, right? And or the inductor or resistor or transistor. As we get into RF and especially in microwaves, then we realize that the wavelengths become significant compared to the dimensions of our circuits. And we have to start looking at things in terms of a wave propagating instead of just lumped element. You need to do that on a high speed printed circuit board for a modern computer, right? So it's operating at gigahertz level signaling, and Therefore, that wavelength of that signal is significant compared to the dimensions of your circuit board. So you have to account for spatial element also. Um, we we often kind of assume that our signals are infinitely long, right? That they're noise free, or maybe if they have noise, it's just additive white Gaussian noise. We've already talked about equal probable symbols versus non equal probable symbols, and uniform sampling, that your sampling rate is exactly at t is equal to cap n times capital T, right? And that you're always sampling that uniformly, and your sampling time is always perfect, right? Well, that isn't always the case, right? So um, oftentimes we're still making some simplifying assumptions, but you should develop an awareness that you're making these assumptions and what the implications are, right? Okay, so let's dive in now to really the topic of this lecture. So all that kind of sets this up. Excuse me. So we talked about channel characteristics, right? So we transmit a signal, then that moves the signal in probably in a form of a wave, moves from the transmitter to the receiver through what we call the channel. In wireless communications, that's typically free space, but it could be a twisted pair of wire, it could be a coaxial cable, it could be a fiber optic, it could be a waveguide, which would be like a metal tube that you would constrain the wave to. So all these type of things are examples of different channels, right? So a channel needs to carry the information encoded on the signals to the distant receiver. Now, your practical basis, we must also provide for the simultaneous use by many other users, right? We can't just be arrogant and say, I own all the channels in the world and no one else can use them, right? So it's a finite resource. There's only so much spectrum that's useful for a given application. For example, certain cell phone signals in the VHF and UHF range, maybe 700 megahertz. Those waves penetrate into buildings, whether houses or offices or commercial structures or whatever. They penetrate the walls pretty well, right? Whereas cell phone signals in, let's say, 1.8 gigahertz or 2.4 gigahertz or so, they they don't penetrate into buildings as well. So you can be sitting in classroom, in your office, or at home, and if your cell phone's operating on one of those high bands, it may not have as good a reception indoors, right? So that's just one example of how certain spectrum is useful for different things, right? But there's only so much spectrum in that region, so that's kind of constrained resource, right? So we got to figure out how can we most effectively share that. So for the last couple of decades, that's been the big deal in wireless communication, is trying to maximize spectral efficiency, trying to use the spectrum as efficiently as possible. So all right. So, what have we said about channels so far? So, we've uh, talked about that maybe they're linear time invariant. They will have some noise. Let's see. There's some. Let's go back and look here. They will have the path length can affect the phase at the receiver, right? We talked about that as being one of the noise sources, right? So we can have multipath interference where our signals might reflect off of walls or buildings or mountains or cars or whatever, right? And so you might have a reflection that still gets to the receiver antenna, but because it's reflected, it's goes a little bit farther than a straight line distance, or maybe a different reflected distance, right? So each of those propagates a little bit different length, and therefore they add constructively or deconstructively at the receiver antenna based upon the phase of that signal, right? So you probably looked at interference effects in a physics course at some point, right? So um, we need to fit in this allocated portion of the spectrum that meets our needs, especially for the transmission distance or this issue of penetrating buildings or that type of thing, right? And then we need to deal with interference from other users. So we touched on a little bit all these things, but there's some things that are even more sophisticated. We have Doppler effects, right? So if you're um, uh, in a moving car and you're on your cell phone, the base station antenna is fixed, but you're moving. Therefore, there's going to be a little Doppler effect uh, that changes the frequency uh, relative to the base station, right? So when you're transmitting or receiving, there's going to be a Doppler effect. That is bigger on faster moving vehicles, right? So satellites, and particularly low Earth orbit, they're crossing from horizon to horizon in about 10 to 15 minutes, and they orbit the whole Earth in about 90 minutes, right? So those things are moving crazy fast. There's a big Doppler effect then, right? We won't really talk about that in this course. It's a more advanced topic, but it's good to understand that these things exist. Then you have nonlinear effects from power amplifiers. There's also passive intermodulation for maybe a corroded antenna component that maybe doesn't have the perfect conductivity you might assume from, let's say, a copper wire or something like that. That can mean that multiple frequencies mix. And just in the same way we talked about how we use that on purpose in frequency mixers to kind of down convert a signal or up convert a signal. Sometimes that happens when we don't want it to in power amplifiers that are particularly known to be nonlinear. All right, so then so up until now, we've not really talked specifically about the symbol shape, other than we talked about maybe being rectangular in some cases, right? But I was kind of purposely vague about that symbol shape, and that might have been frustrating at times. But because I'd talk about these orthonormal basis functions and making up pulses, but I would not get real specific about them, right? So, and that's because all up until now we've been assuming that our channel has infinite bandwidth. We've not limited the bandwidth of the channel, meaning that we can put in whatever shape pulse we get, and that pulse might have infinite bandwidth in it, right? That rectangular pulse has an infinite number of odd harmonics, right? And that would require an infinite bandwidth of the channel. But reality means that practical channels are band limited. On the one hand, they're band limited by regulation, right? We're only allowed to transmit over a finite range of spectrum. But also, from a practical basis, we cannot build antennas that have infinite bandwidth. We cannot build power amplifiers that have infinite bandwidth, or low noise amplifiers on a receiver side that have infinite bandwidth. Everything has some bandwidth associated with it, right? So now that means that in reality, our channel is band limited, right? So we view the channel as a filter, right? With an impulse response HT or corresponding spectral response of H of S, right? So our channel now has some limited bandwidth over which we're operating, and we're going to describe that using this spectral response H of S or H of F if you want, or in the time domain by its impulse response. So we can see that here in that we might be sending in these kind of modulating signals that might be a plus A here and a minus A there. And then we're sending in these impulses into the pulse shaping filter of the transmitter, right? So now maybe we naively assume that this would produce a rectangular pulse, right, as its impulse response. So we put in an impulse here, and we would get out a rectangular pulse. And maybe this case it would be a positive rectangle, and in these two cases it would be a negative rectangle, maybe with an amplitude of A or something, right? So then we will have the impulse response of the channel itself, right? So now that channel could be our free space, it could be our antenna bandwidth, it could be the bandwidth of our power amplifier. But ultimately, since we are constrained by regulation, we probably have some filters put in there on purpose to in our transmitter at that transmission stage to filter out any signals that might be outside of our allowed operating spectral region, right? So we wrap all that in this channel impulse response, right? Then we know we get some noise added at the receiver, at the input of the receiver, and then the receiver also has its own impulse response. Maybe we're using a match filter type receiver where we're now matching this to this spectral shape, right? And then we sample it and we do some thresholding operations out here, right? So here we can write out that Y out here, or maybe right here, because I'm not showing the sampling or thresholding, right? But the output of this part of the system would be all of this convolved here, the input symbol here, then where we've represented this with impulses because we're kind of separating out the pulse shaping with the symbol mapping and stuff. So then we convolve that with the transmitter pulse shape and the channel and a receiver, but then we're also adding in this noise. Now note that this noise actually gets filtered by the receiver, right? So if we start off with AWGN white noise, right? White means that infinite spectrum, right? Now we end up with filtered noise. This will become important later when we have to deal with the fact that, oh, by the time we're actually getting to this output here, our noise really isn't AWGN anymore. Sometimes we call it pink or colored noise, or it's just filtered noise, right? So it's no longer has this infinitely wide spectrum, power spectral density. All right, so so hopefully by now you're starting to pick up that, wow, using rectangular pulses in the time domain is going to be a problem, right? Because this Fourier series expansion of this rect is this infinite number of odd harmonics at decreasing amplitudes, right? It would take an infinite bandwidth to support that. We know we don't have that infinite bandwidth. We've got a finite bandwidth, which means that we're going to lose some energy out of this, right? And then if we're attenuating or rejecting some of the higher frequency components of this, then we no longer are going to have this nice square or rectangular pulse in the time domain, right? So if we take this ideal rectangular, then we filter out some of those odd harmonics to it, and then we kind of take that Fourier series expansion and try to look at what that filtered time domain is. It cannot be a rectangular function anymore, right? So because we've gotten rid of some of that energy. So uh, so also in general, again, this is kind of repeating some of that stuff I had in those first few slides. Things that change fast in a time domain, in other words, steep slope, require wide bandwidth to reproduce, right? So hopefully that's kind of stuck in your mind now. So we can assume a flat channel, a rectangle system symbol here. And so we end up with this sine x over x in the frequency domain. This, oops, did I go the right direction? This is direction I want to go. Okay, so this brings us to the problem, what we call intersymbol interference, right? So we often abbreviate that with just ISI. So this occurs when we have finite bandwidth available to our pulses, right? And the effect is that the impulse or the response of the channel causes the time domain of the symbol to leak out of its strict 0 to t boundaries and affect adjacent symbols, right? So we're going back to this kind of abstract concept where things that are bounded in the time domain are unbounded in the frequency domain, but things that are bounded in the frequency domain end up being unbounded in the time domain, right? So now we have this band limited channel, right? Now we're binding things in the frequency domain. We're saying that no, you're not going to have energy out at plus and minus infinity frequencies, right? We're going to put a limit on that. That necessarily means that our time domain is going to be infinite now. Okay, so I mean, these infinite things are maybe never really real in practice, right? But the fundamental idea here is that we're binding the energy in the frequency domain, and therefore we're going to have energy that smears out, that spreads out in the time domain. And so here that's going to affect adjacent symbols. So if we send a symbol in the time domain, now it doesn't just stop at t. It's going to have some energy that's leaking out, and it's going to ring a little bit, right? And that means that that energy is still going to be around when our next symbol comes along, right? So now, one of the ways that we can visualize this is eye diagrams, and your book has a section on that. If I've updated the reading assignment on Moodle to give you some guidance on where to read in the book for this, but it's kind of in the middle of chapter 6. And eye diagrams are this visualization tool to study how the channel affects the receiver's ability to accurately measure a pulse. And we use this eye diagram at all levels of digital transmission and reception, right? So if you're an embedded engineer and you're looking at sampling some signals, then on some IO, maybe you're doing some FPGA work in a super high speed data center that's trying to send data around very fast, like in machine learning type applications with a GPU farm and that type of thing, right? So now you are going to be using eye diagrams to understand the impact of the bandwidth of all those interconnects between your computers or computer components, right? But it's used at all levels of digital transmission and reception. So you can kind of go through all this here. You may have seen this before in your embedded systems course. I'm not sure. I used to teach that course and would talk about this a little bit, but I'm not going to belabor this a whole lot, but the idea here is that this overlaps a whole bunch of different pulses, right? Where maybe you don't have a change in value from one sampling instance to another, so you stay high, or maybe you stay low, or maybe you transition, and you're transitioning at a particular slew rate, and then you might transition again, or maybe you come up here and you stay high, right? So you overlap a whole bunch of pseudo-random type of transitions, and then you look at this, right? This kind of looks like a person's eye, right? So you want this eye to be open, right? You see here that these things have some, distortion to them, some noise associated with it, and that type of thing, right? So the more noise you have, right? So or distortion, then the wider this area will be, and then smaller this eye will be. In the worst case, the eye closes, and it's becomes impossible to determine whether a signal is high or low, right? So here's our zero crossing points. In electrical circuit, it's sometimes easiest to measure when things cross through zero. You can use a little comparator circuit to do that. And so a lot of times we'll generate our timing based upon looking at zero crossings, right? And if we're on a receiver, we're trying to figure out, okay, what was that transmitter clock like, right? So we can synchronize to it by looking at these zero crossings and try to regenerate a clock based upon that, right? So the tighter the zero crossing is, the less jitter we will have. This jitter is this kind of time uncertainty in trying to recover that time, right? But then we will generally want to sample here where it's the signals have had a chance to move from low to high or high to low or whatever, right? So these can actually be stacked up to multiple different levels. This is just showing a binary type of coding system. So we'd like to sample right there, and we'd like this eye to be very much open. So this is a type of thing you would use on the bench, on the test bench, or you would be examining in your simulator system, that type of thing. Right? So, all right. So now let's look at our pulse characteristics. And another thing we've kind of done is we've kind of looked at pulses in isolation, right? We've looked at, when we have looked at a pulse, we're just assuming that there's like one pulse, right? And here we start to deal with multiple pulses over and over and over again, right? So how do we deal with that mathematically, right? So first, let's assume our channel is band limited, but has otherwise ideal characteristics, all right? So there's lots of other things that can go wrong in a channel that we have to deal with, but for now, we're just going to assume that it's band limited. So we can write this frequency response of the channel as being 1 through a range of frequencies, absolute frequencies less than its bandwidth W, right? So this might be centered at DC or offset somewhere, but in maybe it's centered around 2.45 gigahertz or or something like that, right? But there's some bandwidth where it's ideally 1 is perfectly flat and otherwise 0. All right. So this is again an ideal filter. Can't build this thing in real life, but let's assume that that's what our channel characteristics are. We want to find a pulse that produces 0 ISI. Right. So let's kind of approach this mathematically. Here we have this IK, right? So this I is the pulse that we're really interested in, right? But because we have this band limited situation, we have these other pulses where n is not equal to k from 0 to infinity, right? And then we're also going to have some noise added to that, right? So we start using this VK here for the noise. But what it's trying to represent is all the portions of the other pulses that are have that leaking time domain signal out there, right? So we'll show a figure here in a few seconds that will help clarify this, right? So we want to satisfy this condition where t is equal to this kt. We define this xk where it's 1 at k is equal to 0 and 0 at k not equal to 0, right? So let's now refer back to our friend Nyquist. He has 3 different criteria for 0 ISI, right? So that this contribution to the output signal will be 0, right? Now we have non-zero amplitude at its center of the pulse. Center, now we're speaking in the time domain, t is equal to 0, and 0 amplitudes at plus or minus integer number of these bit periods. Okay, so we can write that in mathematical form here as a 1 at t is equal to 0 and 0 elsewhere. In between these times, all right, we'll figure that out. Okay, we're not constraining that. We're constraining at these very specific times. T is equal to 0 and plus or minus n times t sub b, where this t sub b is the reciprocal of your bit rate, right? So it's your bit period. All right, so that's a lot of weird equations right now. This can lead to a pulse, right? So we're just going to say that this is our criteria that will mean that these other pulses won't have any impact on our P of t, right? So it's essentially saying that these terms all sum to 0 at the specific instance of time, right, for a particular pulse. And as it turns out, this leads to a particular type of pulse, a sync pulse, sync in the time domain, right, with these features here. And again, we're kind of repeating this, right? Nyquist criterion. And we're going to see here that the sync meets this, right? And we can note that the frequency response to this pulse is this rectangular function, right? Sync x in the time domain is going to be now a rectangular function in the frequency domain, right? So you may have studied kind of the vice versa. A rectangular function in the time domain is a sync function in the frequency domain. That's probably it's a classical problem you look at in when you learn about Fourier transforms and frequency response and stuff, right? So here we're kind of saying, let's do a sinc in the time domain, and that leads to a rectangle function in the frequency domain. So what does that look like here? Now we have these sinc x's, right? So here's maybe the pulse that we're interested in, but we've got other pulses, right? So now these would all be, let's say, plus A, right? But this one, it's drawn this way just for convenience, but it could be a negative pulse or plus A, or it could be like you could have a different amplitude levels in a more complex constellation, right? But the idea here is that you're going to have a sinc x over x pulse here. This is our one that we're focused on right now, but we've got to understand that there were some previous or succeeding pulses, right, at other times. Right? As time goes on, we'll have another pulse. Well, look at what happens at these sampling instances, right? These guys all cross zero at this integer multiple of this bit period, right? So here we send one bit, we send another bit, we send another bit, we send another bit. But these guys now spread out in time, meaning that they're bounded in frequency domain, right? But they're at these integer number of sampling instances. These other samples, these other pulses have zero energy. So they're not interfering with these other guys, right? So this is what we're talking about with intersymbol interference, right? These are intersymbols, different symbols, and are they interfering with each other? Well, Nyquist says that if you set this to have zero energy at these other sampling instances, then no, you won't have intersymbol interference. If we sample here, we're only getting the effects of this pulse. We're not getting any energy from these other pulses. If we sample here for this pulse, everyone else is zero at that point, right? And so we're able to sample without any interference from any of these other pulses. And the pulse is bounded in spectrum. Okay. So now that you've seen this, as you kind of review this lecture, now go back and look at some of these slides, right? And try to relate all of them, right? But this is kind of the money slide here is what we're saying is that we want this pulse to cross zero at these others. And as it turns out, the sinc x type function does that, right? It meets the Nyquist first criteria. And it is also bounded in frequency. Right? So, well, okay, you've already figured out that that's easier said than done. That pulse starts at time equals t minus infinity. Oh, did you remember to start all your pulses at infinite negative time? Of course not, right? So if we started them now, we'd have to wait for infinity for any of this to actually make effect, right? That make the effect we want. So starting our pulse at any time greater than minus infinity means that we're going to have some spectral leakage, right? So we're not going to be constrained here because we didn't actually start every pulse we ever needed in the world at any time is equal to minus infinity. It's an impossibility, right? So all right, so we're already going to deal with some non-idealities here. So the decay in the time domain is slow also for a sinc x function, right? So these, what we call time side lobes, are still kind of big, right? We'd like them to be smaller, ideally, these guys here. So why is that a concern? Well, the waveform is kind of steep in that vicinity of the ideal sampling instances, and any mistiming will lead to significant energy, right? So we'd like to time right there and like to time right there, but if we're off by a little bit, then we're going to have a lot of energy for this pulse here contributed by this other pulse and this pulse and that type of thing, right? So because it's so steep in that region, so we got to be exact, and that's really, really hard to do, right? So we've got some real issues, and yeah, this is mathematically ideal, but on a practical basis, it's not going to work for us. So the idea here is to now allow for some controlled excess bandwidth, right? So now we don't want our bandwidth to go out to infinity, right? But let's let it leak out a little bit, right? So ideally, if we were dealing with this sync x over x function, we could squeeze everything into this 1/2 of the rate of the bit rate in a plus or minus 1/2 of the bit rate in the frequency domain, right? We could constrain all our energy into that with this ideal sync function. But let's allow some energy to leak out of that, but not forever, right? So we see that here, right? It's not a rectangle, but it's kind of a smoothed out rectangle, let's say, right? So now we could have channels next to us in the frequency. So we call this a raised cosine filter, right? So something that meets this type of shape. And we consider constraint that the peaks of the subsequent pulses still align with the nulls of the impulse responses of the other pulses, right? So this is still this Nyquist first criteria, right? So we go back to this criteria that we got all the energy here at our sampling instant, but everywhere else we've got zero energy, right? So we still want to satisfy that, right? But we also desire the slope near the sampling points to be shallow to minimize the impact of timing errors. The raised cosine filter meets these requirements, commonly implemented as a root raised cosine filter with half on the transmit side and half on the receive side, right? So when we say this, it's like, if you remember that if you take things in the frequency domain, we can kind of multiply them together, right, to cascade some responses. Well, if we take the square root of this ideal raised cosine filter and put that on the transmit side, transmit filter, and then we take the same filter, square root, put it on the receive side. Now, when we multiply those in the frequency domain to get the overall frequency response, then we get the square root times the square root gives us the actual value of the raised cosine filter. All right, so what does that mean here? This is the raised cosine in the frequency domain. We're looking at half of it, right? So the positive frequency. So it's going to be flat out to a certain frequency, and then it's going to roll off, right, down to here. Now, technically, the raised cosine spectrum is a family of filters, right? And so we see that here or here. In the limit, you can make it a square filter, in which case you would have a sine x over x in the time domain, but you can allow energy to leak out up to twice the minimum frequency, right? Again, we're only showing the positive frequencies here, right? So ideally, technically, we could fit in here on this RB over 2. But if we let it leak out there, now we have this kind of very shallow filter. And we see, if you kind of match up, these time side lobes become very, very flat. So any mistiming here is only going to have a little tiny bit of energy introduced into it, right? So this is the equation. The book goes and derives that. I'm not going to do that. The point here is that this can be parameterized for different roll-off factors, right? So, all right, I think I'm at the end. Everyone have a great spring break. Hopefully you can use it to, as I say, get all rejuvenated and relaxed. If you're behind, now's a good time to get caught up. So, and be safe. Take care. See you in a couple of weeks.
Thank you, Professor.
Mhm.
Thank you.